We know that if we connect a p-n junction diode to a battery with the p side connected to the negative terminal and the n side connected to the positive terminal, the diode is said to be reverse biased. A reverse biased diode allows little or no current through it. According to the IV characteristic of a p-n junction diode, the current through a reverse biased diode changes very little with an increase in applied voltage, and it remains almost constant. The value of this current is called the reverse saturation current. Let us see what happens when we increase the applied voltage across a reverse biased diode after it attains the reverse saturation current stage. We observe that the current through the reverse biased diode suddenly increases for a specific value of applied voltage. This phenomenon is called breakdown of the diode. Diode breakdown occurs because a high applied voltage creates a strong electric field that results in the breakage of covalent bonds in the p region. The electrons released by this breakage of bonds have enough energy to enter the n region, resulting in a large increase in current through the diode. The emission of these electrons from the host atoms due to the high applied voltage is called the internal field emission or field ionization. The voltage at which there is a sudden increase in current in a reverse biased diode is called the breakdown voltage. A diode designed to have low breakdown voltage under reverse bias is called a Zener diode, which is named after its inventor C. Zener. A Zener diode is made by doping both the p and n sides of a p-n junction diode heavily. The circuit symbol of a Zener diode is represented as shown. Although it is similar to that of a p-n junction diode, the major difference is that the two small projections in opposite directions are added to the line on the n side of the p-n junction circuit symbol. The pointed edge of the triangle indicates the n side of the diode, and the base of the triangle indicates its p side. Beyond the breakdown voltage, even an insignificant change in the reverse bias voltage can produce a significantly large change in the current. This implies that the voltage across the Zener diode remains constant, even though the current through it varies widely. Thus, a Zener diode can be used as a voltage regulator to convert a variable voltage input into a constant voltage output. Here is a simple circuit used for converting a variable voltage input, say, from a rectifier into a constant voltage output using a Zener diode. The input voltage is connected to the Zener diode through a series resistor having resistance R with the Zener diode in a reverse bias arrangement. A load resistance is connected parallel to the Zener diode to collect the constant voltage output across it. The current through R is equal to the sum of the Zener current and load current. If the input voltage in the circuit is increased, the current through R and the Zener diode increases. This causes an increase in voltage across R without a change in voltage across the Zener diode. This is due to the fact that beyond the breakdown voltage, the voltage across the Zener diode remains the same, although the current through it changes. On the other hand, if the input voltage is decreased, the current through R and the Zener diode decreases. This reduces the voltage across R without affecting the voltage across the Zener diode. Thus, irrespective of increase or decrease in the input voltage, the voltage across the Zener diode remains constant, which is collected across the load resistance. Hence, the Zener diode acts like a voltage regulator. The choice of the Zener diode depends on the required output voltage. Zener diodes are available with output voltages ranging from a few volts to hundreds of volts. In order to provide good voltage regulation, it is essential that the current through the Zener diode is several times higher than the load current. This is done by selecting a suitable series resistance R that ensures Zener current in the circuit is several times higher than the load current. Optoelectronic junction devices are PN junction devices which work because of the current carriers that are generated by photons. Photodiodes, light-emitting diodes, which are referred to as LEDs in short, and solar cells are examples of optoelectronic devices. A photodiode is a device that is used to detect optical signals. It is a photodiode in your TV set that allows you to operate your TV using a remote. A photodiode is a specially fabricated PN junction diode with a transparent window that allows light to be incident on the diode. We know that light consists of tiny bundles of energy called photons, whose energy in turn depends on the frequency of the light. We also know that electrons in the semiconductor atoms of a diode need to overcome an energy gap to become free and create electron-hole pairs that act as charge carriers in the diode. When photons of light with energy greater than the energy gap fall on the diode, the photons get absorbed by the semiconductor atoms, leading to the creation of electron-hole pairs in the diode. A photodiode is designed so that the maximum number of electron-hole pairs is created in the depletion region around the PN junction. We know that the depletion region has an electric field created due to the separation of static charges on both sides of the PN junction. As soon as an electron-hole pair is created, the electric field across the depletion region pushes the hole towards the P side and the electron towards the N side. Due to this movement of charge carriers, a small photocurrent is generated through an external load connected across a photodiode. The magnitude of the photocurrent increases with an increase in the intensity of the incident light. However, this change is too small to be measured in the absence of any external bias. The magnitude of the photocurrent is too small compared to the large current that flows through the diode under forward bias. Thus, the change in photocurrent with change in the intensity of light is very difficult to measure when a diode is operated under forward bias. However, the change in the magnitude of the photocurrent with the intensity of the incident light can be measured when a small current flows through the diode under reverse bias. Thus, a photodiode is always operated under reverse bias. The IV characteristics of a reverse biased photodiode for different intensities of incident light are shown here. A light-emitting diode, or an LED, is a device that produces photons of different frequencies of light. An LED is a specially fabricated, heavily doped PN junction diode encased in a transparent cover which allows the emitted light to shine through. An LED is operated under forward bias, which increases the diffusion of minority charge carriers across the p-n junction. This leads to the recombination of the electron-hole pairs, which results in the liberation of energy in the form of photons. The energy of the emitted photons and the color of the light produced depends on the nature and the band gap of the semiconductor material used in the LED. Here is a list of some semiconductor materials used in LEDs of different colors. LEDs offer several advantages listed here over conventional electrical light sources: low operational voltage and power consumption, instant on-off switching without any warm-up time, source of near monochromatic light, long life and negligible wear and tear. LEDs have low reverse bias breakdown voltages. Thus, care must be taken that they do not get connected in reverse bias across a high voltage source. Now let us consider a solar cell. A solar cell is a device that converts light energy into electrical energy. The solar panels that you see connected to solar power appliances are made of a large number of individual solar cells. A solar cell consists of a thin, flat wafer of p-type semiconductor on which a very thin layer of n-type semiconductor is grown to create a p-n junction with a large surface area. The back of the p side is coated with a metal to form a metallic back contact. The top of the n side is provided with a metallic grid contact that covers only a small percentage of the total exposed area of the cell. A solar cell works when light is incident on it from the top over the n side of the device. A solar cell works on the same principle as that of a photodiode, where incident light generates electron-hole pairs in the depletion region of the p-n junction. As in a photodiode, the holes are pushed towards the p side and electrons are pushed towards the n side due to the electric field in the depletion region of the solar cell. The holes pushed towards the p side are collected by the back contact, while the electrons pushed towards the n side are collected by the grid contact. This collection of charges makes the back contact positive and the grid contact negative and gives rise to a current when a load is connected between the two. Unlike a photodiode, a solar cell works without any external bias. The large surface area of the p-n junction in a solar cell generates measurable photocurrent, making it a source of electricity. However, just like a photodiode, the photocurrent produced by a solar cell depends on the intensity of the incident light. If we plot the intensity of solar radiation against its energy, we find that the maximum intensity radiation is produced by photons having energy equivalent to 1.5 electron volts. Thus, semiconductors having band gaps lower than 1.5 electron volts are used in the manufacturing of solar cells. Here are a few examples. In semiconductors having band gaps higher than 1.5 electron volts, only a small portion of the total solar radiation is used to produce photocurrent. Thus, such materials are not preferred in the making of the solar cells. In semiconductors having band gaps much lower than 1.5 electron volts, most of the incident radiation is absorbed by the top layer of the cell. Thus, very little radiation reaches the depletion region to produce electron-hole pairs that gives rise to the photocurrent. Hence, such materials are also not preferred in the making of the solar cells. Besides band gap, the other criteria for selection of suitable material for solar cells include high solar radiation absorption capability, good electrical conductivity, and ease of availability and cost. Here, we can see the IV characteristic of a solar cell, which is drawn in the fourth quadrant, as it does not require any external bias and acts as a source of electricity. A transistor is a semiconductor device used for switching and amplifying electric signals. A point contact transistor was invented by J. Bardeen and Walter Brattain in 1947. The first junction transistor was invented by William Shockley in 1951. There are many different kinds of transistors. However, in this module we will discuss the transistors that contain two back-to-back p-n junctions. Such transistors are called bipolar junction transistors, referred to as BJT in short. When we speak about transistors in general, without reference to any particular kind, we refer to these bipolar junction transistors. There are two types of bipolar junction transistors: the PNP transistor and the NPN transistor. A PNP transistor consists of a smaller, heavily doped P region and a larger, moderately doped P region separated by a thin, lightly doped N region. An NPN transistor consists of a smaller, heavily doped N region and a larger, moderately doped N region separated by a thin, lightly doped P region. The smaller, heavily doped region in a PNP or in an NPN transistor is called the emitter. The emitter supplies a large number of majority charge carriers that are holes in a PNP transistor and electrons in an NPN transistor. The larger, moderately doped region in a PNP or in an NPN transistor is called the collector. The collector collects the major portion of the majority charge carriers provided by the emitter. The thin, lightly doped region in a PNP or in an NPN transistor that separates the emitter and collector is called the base. Connecting terminals are provided for the emitter, the collector, and the base. Thus, a transistor is a three-terminal device. Suitable potential difference must be applied across both the p-n junctions to operate a transistor. This process is called biasing the transistor. To bias the two p-n junctions in the transistor, we require a pair of terminals for each p-n junction. Thus, in total, we require 4 terminals. But the transistor has only 3 terminals. Hence, one of the terminals is made a common terminal to bias the two p-n junctions. The emitter, or the base, or the collector can act as the common terminal, and biasing on this information, the configuration of the transistor is named accordingly. In this module, we discuss about transistors in common base configuration. During biasing, normally the PN junction between the emitter and the base is forward biased, while the PN junction between the base and the collector is reverse biased. The reasons for adopting such a biasing scheme for the two junctions will be discussed at the appropriate juncture in the course. A transistor with its emitter base junction forward biased and base collector junction reverse biased is said to be in an active state. Before we discuss the working of PNP and NPN transistors in the active state, let us recall that by convention, the direction of electric current is taken opposite to the direction of the flow of electrons, that is, in the same direction of the flow of holes. When the emitter base junction of a PNP transistor is forward biased, a large number of holes from the emitter enter the base. This large flow of holes from the emitter to the base constitutes the emitter current. This current is equal to the current entering the emitter from the emitter terminal connected to the battery. Since the base is very thin and the base collector junction is reverse biased, most of the holes entering the base reach the collector terminal, forming the collector current. Only a very small portion of the holes entering the base reach the base terminal, forming a small base current. A PNP transistor is represented by the symbol as shown. Note that the direction of the arrow indicates that in a PNP transistor, current is directed from the emitter to the base. Similarly, when the emitter base junction of an NPN transistor is forward biased, a large number of electrons from the emitter enter the base. This large flow of electrons from the emitter to the base constitutes the emitter current, opposite in direction to the flow of electrons. This current is equal to the current leaving the emitter from the emitter terminal connected to the battery. Since the base is very thin and the base collector junction is reverse biased, most of the electrons entering the base reach the collector terminal constituting the collector current. Only a very small portion of the electrons entering the base reach the base terminal, forming a small base current. An NPN transistor is represented by the symbol as shown. Note that the direction of the arrow indicates that in an NPN transistor, current is directed from the base to the emitter. As per Kirchhoff's law, in both PNP and NPN transistors, the emitter current is equal to the sum of the base current and collector current. Note that in both cases, the base current is very small compared to the emitter current. Thus, the emitter and the collector currents are nearly equal. In the circuits we discussed so far about transistors in the common base configuration. We will discuss later about different types of configurations and their uses. You have learned that there are two types of bipolar junction transistors, namely the PNP transistors and the NPN transistors. You have also learned that a transistor is said to be in active state when its emitter base junction is forward biased and base collector junction is reverse biased. While biasing a transistor, the forward biased connection is called the input circuit and the reverse biased connection is called the output circuit. Since a transistor is a three-terminal device, one of its terminals is common to both input and output. This gives rise to three transistor circuit configurations. When the base of a transistor is common to the input and output, the transistor is said to be in the common base configuration. In this case, the input voltage is represented as VEE and the output voltage is represented as VCC. When the emitter of a transistor is common to the input and output, the transistor is said to be in the common emitter configuration. In this case, the input voltage is represented as VBB and the output voltage is represented as VCC. When the collector of a transistor is common to the input and output, the transistor is said to be in the common collector configuration. In this case, the input voltage is represented as VBB and the output voltage is represented as VEE. Since the NPN silicon transistor is the most commonly used transistor and the common emitter configuration is the most commonly used circuit configuration, let us study the input and output characteristics of an NPN transistor in the common emitter configuration. The circuit to study the input and output characteristics of an NPN transistor in the common emitter configuration is as shown. In the common emitter configuration, the input is between the base and the emitter and the output is between the collector and the emitter. The variation of base current, IB, with the base emitter voltage, VBE, is referred to as the input characteristics, and the variation of collector current, IC, with the collector emitter voltage, VCE, is referred to as the output characteristics. The input characteristics of an NPN transistor in the common emitter configuration can be studied by plotting the base current, IB, against the base emitter voltage, VBE, at a constant collector emitter voltage, VCE. The collector emitter voltage, VCE, is kept constant within the range of 3 volts to 20 volts to ensure that the collector base junction is reverse biased and the transistor is in active state. Since the common emitter voltage, VCE, is the sum of the common base voltage, VCB, and the base emitter voltage, VBE, and the base emitter voltage, VBE, is 0.6 volts for a silicon transistor, the collector emitter voltage is sufficiently larger than 0.6 volts. An increase in the collector emitter voltage, VCE, appears with an increase in the collector base voltage, VCB, keeping the base emitter voltage, VBE, constant. Thus, the effect on the base current IB is negligible. Hence, the different constant values of the collector emitter voltages, VCE, gives almost identical curves for the input characteristics. The input characteristics can be used to calculate the input resistance. The input resistance, Ri, is defined as the ratio of the change in the base emitter voltage, delta VBE, to the resulting change in the base current, delta IB, at a constant collector emitter voltage, VCE. The input resistance is referred to as a dynamic resistance and is of the order of a few hundred ohms to a few thousand ohms. The output characteristics of an NPN transistor in common emitter configuration can be studied by plotting the collector current IC against collector base voltage VCE at a constant base current IB. Since the base emitter junction is in forward bias, a small increase in the base emitter voltage VBE increases the whole current from the emitter and the electron current from the base. As a result, the base current IB and the collector current IC increase proportionately. Thus, the different constant values of the base current IB give different output characteristics as shown here. The output characteristics can be used to calculate the output resistance. The output resistance, RO, is defined as the ratio of the change in the collector emitter voltage, delta VCE, to the change in the collector current, delta IC, at a constant base current IB. Since the base collector junction is reverse biased, the output resistance is very high and is of order of a few hundred kilo ohms. The current amplification factor, beta, of a transistor is defined as the ratio of the change in the collector current, delta IC, to the change in base current, delta IB, at a constant collector emitter voltage, VCE. The AC current amplification factor is also known as the small signal current gain. Its value is very large since a large change in the collector current results in a very small change in the base current. The ratio between the absolute values of the collector current IC and the base current IB is called the DC current amplification factor. The values of the AC current amplification factor and the DC current amplification factor are almost equal.